Merci.
Welcome to the afternoon session. Our next speaker is Veronika Hubeny. She will talk about entanglement entropy relation from holography.
Okay, thank you very much. Well, it's a great pleasure to be here, and I thank the organizers for inviting me. In fact, they're making me work, so I'll give another talk next week. How is the volume? It's fine? Okay. All right, so this will be on work in progress with Mukund Rangamani and Max Rota, who's been the driver of this project very much, so all the hard questions should go to Max. And Max is right now a postdoc in UCSB and will be on the market in the fall. Okay, so this will be about entanglement in sort of context of, well, motivated partly by holography. Well, so as you all know, the sort of structure of entanglement is very useful quantity to study. I mean, it gives us nice characterization of the state and sort of the dynamics of any quantum system. And in the recent years, we have sort of come to realize that it might be very sort of play a fundamental role in sort of understanding the workings of holography. Okay, so the quantities, well, a very useful measure of entanglement is the entanglement entropy. And it's a very natural one, but in the context of holography, of course, we have to contend with the fact that the entanglement entropies can be infinite. We have to sort of understand what to do about that. And so natural things that one can study is combinations of entanglement entropies for different sort of partitions, which can be finite. Okay, so those will be the things that we will consider. And then they can form very interesting quantities that have some independent information theoretic meaning, and such as sort of the mutual information, which is the amount of correlations between sort of two subsystems, and sort of the multipartite generalizations of that. And since these quantities can be finite, it's then meaningful to ask whether they're, say, positive or negative or zero. And that information is then useful to give us some lessons about this sort of structure of entanglement. And so, in particular, we want to consider the relations, you know, the inequalities or equalities for such linear combinations of entanglement entropies, and in particular sort of the saturation of, I mean, such linear combinations of entanglement entropies being zero gives us very nice insight into this entanglement structure. Okay, so this studying these is useful, but only some number of them, or at least a handful of classes, some of these classes are infinite, but it's still a handful of classes which are known. Okay, so the motivation for the talk is to see whether we can generate, in some very natural way, more such entanglement relations. Okay, so that's the plan. Try to figure out an efficient way to motivate linear combinations of entanglement entropies that might have some useful information theoretic meaning. And the tool that we'll use is holography. But before getting to sort of holography, let me just flash some examples of very well-known such relations. Okay, there's some that are completely universal, meaning hold for any quantum state. Some that are not universal, but hold for an interesting subclass of states, such as the ones that would have holographic dual. Okay, so the universal, probably the most simplest universal relation between entanglement entropies is subadditivity, which is saying that entanglement entropy of two different systems, the sum of that is at least as large as the entanglement entropy of the combined system. A, B is sort of the combination of the system A and the system B, the union of them. There's the sort of related inequality, the Araki-Leap inequality. So you can think of these as sort of triangle type inequalities for entanglement. They're the more sort of stronger inequalities, the strong subadditivity, and its cousin, the weak monotonicity. So all these hold for arbitrary quantum states. In holography, there's structurally similar inequality to these, but one that does not hold universally for any quantum state, but does hold for all states that have a holographic dual describing a classical geometry. Okay, so this is the so-called monogamy of mutual information, which I guess you have heard a lot about yesterday, and maybe at other points. There's the sort of generalization if you have multiple parties, say five partitions of Hilbert space. There's a sort of cyclically symmetric generalization of this, and in fact you can do it for any odd number of parties, and so forth. So there's others. These are just examples of some, and not all of those are sort of independent of each other. So for example, in this class of things, the Araki-Leap is just a purification, can be thought of as a purification of the subadditivity, the weak monotonicity can be thought of as a purification of strong subadditivity, and so forth. Furthermore, not all of them are, well, some of these are redundant. So for example, the strong subadditivity, as you can see, by adding these two inequalities up, okay, the SA plus SB cancels out here, the SAB cancels out, and you get the same thing as here up to a relabeling of the parties. So, but because of this relabeling, you get each of these would correspond to a set of relations where you permute what you call A, what you call B, and so forth. Okay, so that's just some examples. But they have nice quantum information theoretic interpretation. So for example, so let me just flash for these basic ones. The subadditivity can be thought of as positivity of mutual information. Mutual information is defined as just the difference between those two sides. And you can think of it as amount of correlation between A and B. The strong subadditivity is the positivity of conditional mutual information. And so its positivity says that this mutual information is monotonic under inclusion. This monogamy of mutual information is the statement of negativity of this tripartite information, which is sort of a super extensivity of mutual information, and so forth. So saturating these things has a meaning. So if mutual information is zero, then that means the two systems are completely uncorrelated. If the conditional mutual information is zero, then that means that you can think of it, these parties as sort of a Markov chain. If this one is saturated, it means that the mutual information is precisely extensive, and so forth. Okay, so this then gives a sort of nice, the fact that some of these things are hold universally in holography, then gives us interesting lessons into the structure of entanglement for any such states, okay, which was already explored in various works in the past, and is still a very interesting question to pursue. Okay, so as you probably all have seen this many times, in holography we can describe the entanglement entropy by just a very simple geometrical object. So in a quantum field theory, boundary where the quantum field theory lives, it's natural to sort of partition the system into just spatial regions, and then the entanglement entropy corresponding to this spatial region would be the area of a minimal surface that's homologous to this region. And if you have so that's for static situations. If you have time dependence, it's easy to so then this would be an extremal surface that's homologous to the region and so forth. Okay, so I'm assuming all of you have seen this. And the proving some of these inequalities is then very, very easy. So, for example, the strong subadditivity, which here I have perversely written in slightly different notation just to maybe make contact with something that you might be more familiar with, is proved very easily by looking at the minimal surfaces, okay, in the static situation, minimal surfaces that would correspond to these boundary regions. Okay, so for example, this is the minimal surface corresponding to this A1 region and so forth. And then the left-hand side is just sum of these two areas, which you can break down into sum of this area and this area. But then those areas are in fact bigger than the areas that would correspond to the minimal surface anchored on that same set of regions, the intersection and the union of these two intervals. Okay, so strong subadditivity follows very straightforwardly. Similarly, if you have a time-dependent situation and you use HRT, well, it's actually was proved first by Aaron Wall using the sort of equivalent so-called maximin description of this extremal surface. But although it's slightly more technical, it still follows very geometrically. Similarly, the monogamy of mutual information proof follows essentially by the same argument, and as Matt and friends sort of made that much more, formalized it much more nicely than what I have just said here in this paper. Okay, but not all of the inequalities can be proved that easily. So for example, in the holographic entropy cone paper, which I'll mention later a little bit, there are other inequalities that these guys obtained, which look more complicated. And those things are not as amenable to the same type of proof, although the inequalities hold, because, well, the subtlety is that both the left-hand side and the right-hand side would have configuration of sort of surfaces which intersect. And so you don't have a nested set of inequalities to use. Okay. So what we want to do is we want to generate easily more such inequalities. And so the plan of the talk is to first describe the sort of framework in which I'll work, the so-called entropy space, sort of introduce it in a simple context, and then motivate sort of the basic objects that we're dealing with, hyperplanes in this entropy space. And then tell you, again, by giving you a simple example of how would we generate these new equalities, or more generally, inequalities, okay? And then summarize. Okay, so let's start with describing this entropy space. Okay, so first of all, so let's do this for the simplest case where you have just two parties. Okay, so you can partition the Hilbert space into a product of two parts, or if you want to, consider a mixed state on this, or you can purify and then consider a pure state on this tripartition. Okay, and then you have a meaningful entanglement entropy for each of these. Okay, so you can meaningfully define the entanglement entropy for the system A, entanglement entropy for the system B, and entanglement entropy for the union of them, which is not necessarily zero if you didn't start with a pure state. Okay, so this entropy vector, which is just the set of all these entanglement entropies that you can define for all these partitions, then lives in what I call the entropy space. Okay, in this case, it's just a three-dimensional space. So you can think of these axes in this way. And the relations then give you various hyperplanes in this entropy space. Okay, so for example, the positivity of any entanglement entropy cannot be negative, tells you that we are working in this positive octant. You know, S of A has to be positive and so forth. Now, we had other relations, so subadditivity tells us that entanglement entropy of A plus that of B must be larger than that of the combined system, and so that means you have to restrict yourself to below this plane. Similarly, the Araki leap inequality tells us that we have to lie above this red plane. And here, you notice this is not symmetric under permuting A and B. And so we have another version of Araki leap, which is just the exchange of A and B. So this inequality, which is just swapping these two axes. So you have to also work above that plane. And now you see that, in fact, the positivity condition is completely redundant once you know these three. And so you don't even have to restrict. I mean, you can just restrict yourself to this cone, which is inside these 3 planes. And in fact, you can think of that cone as defined by the so-called extreme race. Okay, so this is, all of this was defined already in this holographic entropy cone paper, which, okay, sorry, I haven't, I have a reference to it later. Okay, so that's for 2 parties. You can do the same thing for any number of partitions. Okay, so for example, if you have 3 parties, so we have now 3 partitions of the Hilbert space and a purifier. And so now you can define 7 independent entanglement entropies, corresponding to all the combinations of these 3 parties. Okay, so the entropy vector then consists of these 7 numbers. And pretty much the same thing goes through. Now we have some a more general type of information quantities, these entanglement entropy relations, which can be generally written as some linear function of all these entanglement entropies with some coefficients. So these Q's are just some rational coefficients. And the hyperplanes would be then given by this quantity being 0. Okay? So that's what specifies our hyperplanes. And again, the point of the exercise is to try to find meaningful sets of these coefficients Q that give us something interesting. Okay, so for n parties, we can do the same thing. Now we are working in sort of a d-dimensional entropy space where d is 2 to the n minus 1. So that's how many combinations you have of all these combinations of the different parties. And so the entropy vector is a vector in the space, and this information quantity is then sum over all of these d terms as before. And again, we have hyperplane now in this d-dimensional space. Okay, so it's the hyperplane is always a codimension 1. Yeah.
Is it obvious that every relation is going to be a linear combination as opposed to like some polynomial or more general attributes?
Well, so I would turn it around. We are interested in looking for the linear combinations. A priori, it's certainly possible that you would have still some interesting relation for nonlinear expressions of entanglement entropies. You have to be careful whether that's still sensibly regulated and so forth. Okay, so you might worry that none of those things in the holographic context will be sort of physical because you get, you can't balance the divergences, for example, and so forth. But as a logical possibility, I don't know. Does anyone know? Are there interesting relations that people have?
The question also related to that, because you're not saying that every point in this cone, and especially if you have many hyperplanes, is actually
Yes.
Constraints on the relation, but it doesn't mean there always exists a density matrix in a qubits or whatever that realizes this set of, entropies.
Well, so far I haven't said that.
So you're
No,
saying that that is the case?
well, okay. So in this entropy cone, the claim was that yes, that was the case. So far from what I have said, it doesn't logically follow. Okay. So far from what I have said, it does not logically follow. But the claim that there is a realization has been made. Yeah, so I'll get to the important point, which is that for the holographic context, you're never sort of natural, or in the nice set of examples, you're not going to be localized at any point in the entropy space. Okay, so that will already be. So maybe you can re-ask your question later. But there was one more question. Okay. Okay, so the mathematical framework then to deal with these hyperplanes is, so we want to study these hyperplanes, and in fact there's a mathematical framework called arrangement of hyperplanes that one can utilize the machinery from. Now, this is just a picture of a generic arrangement of hyperplanes. In our case, all of the hyperplanes have to go through zero, because, if the regions are all trivial, or the parties are all trivial, then the entanglement entropies are zero. And so the hyperplanes then would form this convex polyhedral cone in the entropy space, and then in the holographic context that was studied by this holographic entropy cone paper. Okay, so now in the quantum field theory context, where you have this decomposition of the Hilbert space very naturally in terms of spatial regions, you have to worry about the UV divergences. So now you have regions that are bounded by entangling surfaces, and because you have a local quantum field theory with sort of degrees of freedom living arbitrarily close to sort of the entangling surfaces, you have this area law sort of divergence. And you can regulate that, but without regulating it, the entanglement entropies for any such object is just infinite. Okay, so you have to worry about what do we do if you're writing a vector in the entropy space, all such entanglement entropies would be out at infinity. Okay, and we have to figure out, well, what does that then mean? Why is it ever useful to talk about an entropy space if our system of interest lives somewhere off of, at the infinite reach of that entropy space? Okay, it's even worse. It doesn't even live at a given point of the sort of the celestial sphere of the entropy space. Okay, so there are two options what one can do. One could try to sort of localize oneself inside the entropy space rather than somewhere off at infinity. One is to just introduce a UV regulator. So here's an example. You have boundary and bulk. Sorry, I switched the directionality here. With, say, two parties. And even though you have a UV infinite entanglement entropy of each of these, corresponding to the fact that this minimal surface has infinite area, you can regulate by introducing a UV regulator so that entanglement entropy you declare to be just counted by the area of these finite bits of the surfaces. Okay. That's nice, but then, so this would give you some finite vector in the entropy space, but now it's cutoff dependent because we can sort of change the cutoff. We don't have to be some fixed cutoff like this. For example, you can decrease the UV cutoff for the region P, and that means that the entanglement entropy is counted by this larger amount of the surface, so it increases even when S of A stays constant. Or I can do the opposite thing and make S of A increase while S of B is constant. So these things, the ratio between the two of them is not fixed, which means that the direction in the entropy space is also not fixed. Okay, so I can get a finite position, but that position is completely meaningless because it's entirely cutoff dependent. Okay, the other option of what I can do to get a finite position of Hilbert space would be to consider a situation which does not have an entangling surface on the boundary at all. But then in order to get a non-zero entanglement entropy, I would need to consider a complicated situation like these multi-boundary wormholes. Again, this figure was taken from the Entropy Korn paper, where you have multiple boundaries and you consider each partition the entire space of a single boundary. Okay, then there is no entangling surface anywhere, and the entropies are finite because they're given by the sort of the necks of this in the bulk geometry. Okay, that's fine, but then we're forced to consider a system consisting of sort of multiple CFTs, which is not the most natural system of interest that one might want to consider. Okay, so that's a problem if we want to consider just a single boundary situation and still talk about our configurations living somewhere in the entropy space. So the natural thing to do instead is not to talk about the individual points in the entropy space, but rather talk about just these hyperplanes. The hyperplanes correspond to these combinations of entanglement entropies that render them finite. So for example, if you have sort of the same number, if you have an inequality with the parties, the same number of the given party occurring on both sides, so that this inequality is balanced, this information quantity would be UV finite, and you can then talk meaningfully about whether it's positive, negative, or zero.
Does it reply to the question before? If you have a nonlinear expression, that's not going to be balanced in terms of divergences?
Yeah, exactly. Yeah. Yeah. So you wouldn't, exactly. So yeah, that's what I had. Yeah. Okay, so so the entanglement, so for example, if you have a subadditivity, okay, then, which is balanced, you have just one A on both sides and one B on both sides, then a saturation of this is independent of the cutoff. So if you take a different cutoff like this, well then you're still counting, you know, this piece of the surface on once on each side and this piece of the surface once on each side. And so the point is then that these hyperplanes are the most natural or fundamental constructs, and that we should really be thinking of the prescription for computing the entanglement entropies not in terms of areas of these surfaces, which are infinite, but rather in terms of the surfaces themselves. Okay, we want to think of this somehow as canceling the surfaces, and then no matter how you slice the surface, that's guaranteed to be zero for a saturation of an inequality like this, because you're canceling the surfaces, not the areas. Okay, so that's the idea. All right, so now I come to how does one generate sort of new quantities? And let me not generate a new quantity, but illustrate how to generate quantities by already generating something that you have seen. All right, which is going to be for 3 parties. Okay, so we actually know the entropy for the 3-party thing completely. And so let's first of all just start as a warm-up by looking at 3 completely uncorrelated regions. So this is the field theory boundary. Here are 3 spatial regions. And the bulk surfaces, which I am going to label them by A, B, and C, are just, those are the only surfaces that come into evaluating the entropy vector. Okay, so then if you want to construct the entropy vector, so S of A, for example, is given by the area of the surface A, okay? So, and nothing times the area of B or C, okay? So in this table, I'll put a 1 when the corresponding entanglement entropy evokes that surface. Okay, so we now get a relation between these coefficients. Okay, so, and you notice that this relation, so if I populate the rest of the table similarly, and then read of the rows, I get a relation. So how does that work? So I have this information quantity. I can rewrite it in terms of the surfaces that were evoked here. I can rearrange, and since this whole quantity is supposed to be 0 for the hyperplane, and I can change my entangling surfaces independently of each other, it must be the case that each coefficient is 0 independently. Okay, so that's how I get all these relations for the entropy cone. Now, in this situation where we didn't have any correlations, we have only 3 equations for 7 unknowns, and so that does not give us a hyperplane. So we need to correlate the region somehow. We need to get more bulk surfaces. So you can still start with just 3 entangling surfaces, but now suppose there is some non-zero mutual information between A and C. So that means we get an extra bulk surface, this arch between the A and C. And I'll just notationally, I denote the surface by which entangling surfaces they're anchored on. So AC means that it has a leg on the entangling surface for A and entangling surface for C. All right, so now we have this entropy table has extra row, and where there used to be a 1 here, there's now a 0. In other words, the entanglement entropy of the region A union C is not counted by this dome plus this dome, but rather by this surface of this arch. So now we get 4 relations, but that's still too little because we still have the 7 unknowns, so we still don't get a hyperplane. Now for notational simplification, I'll just, instead of drawing these bulk surfaces, let me just draw the configuration on the CFT, where I'll denote the mutual information by this link. And we can go all the way and now consider a configuration where everything is sort of correlated. And that gives us 7 bulk surfaces. So you have all these 3 arches, and then you have a sort of 3-legged surface that ends on A, B, and C. So that's this ABC surface. But now you see that you have, in fact, 7 equations for 7 unknowns. So all of these are 0 trivially, so that's no good either. What we really want is 6 relations. So let's try to get rid of 1 surface. So here's another configuration where we have actually 6 entangling surfaces, but also 6 bulk surfaces. And if you do that, we do get a hyperplane because we'll get all these independent relations from each row of this table corresponding to each of these, entangling, or, well, each of these bulk surfaces. And a solution which is easy to check, is that you have some constant, fixed constant times +1 here, and fixed constant times -1 here. So the QA is, say, +1, QB is +1, QAB is -1, and so forth. And so, which you can see by just adding these numbers. So this is 1, -1, and so forth. 1, -1, -1, +1. So all of these rows give you 0. And in fact, those coefficients give you a hyperplane corresponding precisely to the vanishing of the tripartite information, which was the thing that was saturating MMI. But here we use nested regions. In fact, we can do this more simply by not nesting regions, but introducing just these individual correlations between the pairwise regions. So now we in fact get 9 surfaces, but again, well, these are not all independent of each other, as you can check, and I'll leave it for the exercise. But again, the solution for all of these things being 0 simultaneously is, again, the same thing as before. So we again get MMI saturation. All right, so the general criterion is for n parties, we can do the same thing. We want to consider configurations which give us the d -1, the 2 to the n -2, independent relations. And then we need to include all of these parties, and we need to have some amount of correlations, because if you don't have correlations, then you just, any balanced inequality is just automatically saturated. And we also want to generate new things, which means we should avoid sort of localizing ourselves of intersection of multiple hyperplanes. So we'll insist that the configuration doesn't saturate anything that any inequality we already know about. Okay, so the ones that we know about for any given number of parties, we can uplift all the previous relations for n-1 parties by simply using that same relation, which just doesn't evoke one of the n parties in all possible combinations. Or we can combine two things from the n into the corresponding relation from here. Okay. So for example, just you can play this game for arbitrarily complicated thing. This is just to flash what sort of things you can do with 5 parties. You can have some complicated relation like this, and you get very easily, you read off what are the sort of relations we get. Since I'm running out of time, I'm not going to explain this, but you can very easily see what you do when you have sort of the same thing, say, nested in another color. Now these things are all the new stuff that would have changed. But you can systemize this search, okay? So to systemize, you sort of scan over all the configuration classes, you find the sort of the basic building blocks, and then you combine these in all the possible ways to get the hyperplanes, okay? I'm running out of time, so let me just tell you the upshot. So for 3 parties, the only thing that you get is that didn't uplift from 2 parties, which was subadditivity and Araki leaps. The only new thing is the monogamy of mutual information, this I3, this tripartite information. For 4 parties, when you do this exercise, again, you get no new inequalities, as already the entropy cone folks had shown. But it's nice that, for example, when you don't have nesting, you get a new hyperplane which corresponds to a 4-party generalization of this tripartite information. But you can show that either sign is possible. So this is not a valid new relation. And you get 4 more things when you have more nesting. But again, you can show that those don't give you anything new. All right. Moreover, if you don't have any nested regions, you can play this trick very universally for any number of partitions, and you can prove what we call an IN theorem, that the only new relation you get is this generalization of the tripartite information to the parties. Okay, so let me summarize. So the hyperplanes are very natural sort of construct and provide a useful characterization of these information quantities. And the trick is that we're sort of saturating inequalities by canceling surfaces. So it's completely cut off independent object. And so it's sensibly defined even when you have a CFT with single CFT or bulk geometry with a single boundary. And the logic of the construction is equally applicable for any number of parties. Many of the other searches are sort of specific for a given n, for a given number of parties. Here we don't care. The same thing works, except that at each new n the search gets more complicated. But one nice thing is that we avoid generating redundant inequalities. So if you remember at the very beginning, I told you that strong subadditivity was actually just a sum of MMI and monogamy of mutual information and subadditivity. Well, our exercise did not generate strong subadditivity, which is very good. All right. All right. The space, so this is sort of answering one of the early questions, is now explicitly closed in the sense that we are identifying an explicit configuration, but now that lives on a given hyperplane. That's how we're constructing the hyperplanes. And since we cancelled surfaces, this applies equally well to the dynamical situation, to the time-dependent situation, where we would have to use extremal surfaces rather than, minimal surfaces at a constant time. So that means that it should be the case that the RT cone should be the same as the HRT cone. By this, if the cone is given by what's allowed by this on one side, on the physical side of these hyperplanes. All right, so there's a bunch of things that are left to explore. One should figure out how efficient this really is when you have large number of parties, and how many of these levels do you need in that generation. We also didn't use so far sort of adjoining regions. Once one gets a candidate hyperplane, one needs to figure out how to efficiently rule it out in the case when you can have inequality going in both directions. To what extent does this now help us localize ourselves in the entropy space? And most importantly, what are the new insights that we gain from this for realizing the sort of the structure of entanglement that pertains to specifically holographic CFTs that have geometrical dual. Okay, so that's it. Thank you.
Questions, comments?
Another way to address the UV divergence problem would be to use renormalized entropies.
If you use you mean just the separated or what?
As what?
To address the UV divergence would be to use just UV regulated entropies or what?
No, renormalized entropies, like for example, you take the derivative with respect to the size of the region. And
yes, so one can do that. Then yeah, it's not. It might not be the case that. I mean, for many of these, I'm not sure about looking at that construct, but certainly what is true is that it need not be the case that these various inequalities like strong subadditivity actually hold if you regulate to a finite entanglement entropy by various different ways. So this one I have to think about a little bit, but I'm not sure that would be good enough. But
other questions?
So I was slightly confused. It seemed like at the beginning you decided you were only looking at separated regions, but then at some point you were looking at regions that touched each other.
Right, so that's fair enough. So so we are in the full search, we are looking at separated regions for convenience, where the separation can be arbitrarily small, and then you might hope to just recover the situation like what I have had with these nested disks in the limit where the separation goes to 0. In other words, you could think of the regions, if you have, say, A inside B, well, you can have B to be really only going up to here, and there's a space in between them, and you can subsequently take the limit as the space goes to 0. So getting the configuration of the sort that I had, without this space is easy once you consider the separated regions and take the limit. What is harder is things like, when you have, say, 3 regions that would all meet in some cusp like that or something like that.
I mean, what motivated my question is that in configurations like
The
this
top one?
pie one, no, the bottom one,
This one.
you know, there's a lot of information
Yes.
in the tripartite information of that, even though the regions are touching each other. And if you just don't ever consider those, then it seems like you're throwing away, you know, physically meaningful information.
Yes, and that's exactly what was this was the gist of this generalization to adjoining regions cryptic comment. We have not yet analyzed all the richness of what happens in this case. So indeed, certainly what is true already from the exercise where you can take a limit like this, it's easier, well, let me just say more generally, if you do consider adjoining regions, you can get some of these relations more simply. Okay, but in terms of the systematizing the search, it's convenient, so far it was convenient to consider non-adjoining regions, simply for organizational purposes, but indeed there are hints that eventually we do need to take into account the adjoining ones as well.
Okay, let us thank the speaker again.
Oh, that's only